So now we'll have a look at a bit of a demo for volumes of revolution. And as you can see on the screen, we have a curve x squared over 2. And we're looking at the bounds between x equals 1, x equals 2, and also the curve. And we want to just rotate that around the x-axis. And so I'll do a top view first, like this. And then I'll move around and show you. This is kind of what we get. Now, obviously this is just showing the surface. And when we do the integral, the calculation calculates the volume of that whole thing, and we call it a solid, really. This is just showing it as hollow. And you can kind of see what that looks like there, and how we've rotated that around the x-axis. And obviously I can change the bounds to make it maybe 0. Yep, and then so now got something like that, like a spinning top. And that's around the x-axis. Can also do this around the y-axis. And get shapes like this. And as for why we do this sort of integration stuff with cylinders and stuff, we can show you with this sort of demo here. So on the left you can see the curve that we have, and if I just have a look, straighten that out here. Good. And it's showing a section of the curve. And now if we were to rotate that, we're essentially, if we wanted to do a rotation like we did in the last one, and then we wanted to create the volume, we can kind of split it up into individual cylinders. See, like that, stuff like a sort of a cylinder like that. And we just do that for the whole curve. And obviously it's got these cylinders, they've got a radius of the value of the function at that x value, and they've got a width of a certain value, a certain amount of x. And if we just make those that bit of x a lot smaller, make it dx, a tiny change in x, you can see that our volume starts to become more and more accurate until it essentially tends to just the entire solid, like that. And remembering what the volume of a cylinder is, if I just went back here, it's pi r squared, right? And r is just f of x, so pi f of x squared multiplied by the thickness, which is a change in x, and as we make that really small, that becomes dx, which is why we solve that integral as being integral between 2 points, pi, the function squared, times dx.